Separable differential equations. Consider a first-order differential equation. If the variables are separable, the solution is found by integration. The first form is the normal or standard form, while the second form is the differential form. To be able to integrate the equation, each side of the equation must be written in terms of just one variable. Or each term of the equation must be written in terms of just one variable. Example 1. Find the general solution of the differential equation. Solution. The variables of the differential equation are not fully separated. So, divide the whole equation by the factor we want to separate. Rewrite using a property of exponent. Because the coefficient of each differential is in only one variable, we can now proceed with integration. The first term can be integrated using integration by parts. Let u be equal to x, and dv be equal to e to the x dx. Thus, du equals dx, and v equals e to the x. Use the formula of integration by parts. The second term can be integrated using the power rule, while the right side of the equation uses the constant rule. Finally, find the explicit form of the solution, if possible. Note that 2k is also a constant, so write it as c. Hence, this is the general solution of the differential equation. Example 2. Solve the differential equation. Solution. Write each side of the equation in terms of just one variable. First, use the definition of a differential. Then, divide the whole equation by the factor we want to separate. Because each side of the equation is in one variable, integrate both sides of the equation. For the right side, use substitution rule. Let u be 1 plus t squared, which means du equals 2t dt, or t dt equals du over 2. Write the integral in terms of the new variable. Then, integrate both sides using the power rule. It is sufficient to add an arbitrary constant to just one side of the equation. Afterwards, substitute u equals 1 plus t squared. Find an explicit form of the solution, if possible. Note that 2k is also a constant, so write it as C. Thus, this is the general solution of the differential equation. Example 3. Find the particular solution of the differential equation that passes through the point. Solution. Write each side of the equation in terms of just one variable. Use the definition of a differential. Because the factor we want to separate is in the denominator, multiply the whole equation by that factor. Because each side of the equation is in one variable, integrate both sides of the equation. For the right side, use substitution rule. Let w be the square root of x, which means w squared equals x. And 2w dw equals dx. Write the integral in terms of the new variable. Use integration by parts. Let u equals w, and dv equals the sine of w dw. It follows that du equals dw, and v equals the negative cosine of w. Use the formula of integration by parts. Integrate the last integral. Then, substitute w equals the square root of x. To find the particular solution at the given point, use the initial condition x equals pi squared over 4 and y equals 1, and evaluate each term of the equation. Thus, C is negative 4 over 3. Substitute C. Afterwards, write into an explicit solution, if possible. Therefore, this is the particular solution of the differential equation at the given point. Thank you for watching. Please like this video and subscribe to Professor Reginald's channel to get the latest updates.